Here's a pretty common special relativity problem to do with muons. Now, muons are a type of subatomic particle which the IB physics no longer studies particle physics, but this problem is pretty common, so it's still worth exploring. And what we have is cosmic rays, essentially fast-moving protons from supernovas, and they collide with the gases in the upper atmosphere, and these gases break apart. We end up with a whole host of subatomic particles, including muons. Now, muons should decay quite quickly and should not be able to be detected very on the Earth's surface, because they decay very quickly. But because they're moving so fast, under the effects of special relativity, we have time dilation and length contraction to worry about. So we still do detect them on the Earth. Okay, so here's the problem. We've got a bit of a description of these fast-moving muons, which we're going to calculate in question C. And it's saying that in the muons frame of reference, only a short amount of time has passed, so 0.6% of them are still being detected on the Earth's surface from the original amount. So we have a few questions, including some explanation type ones to show you understand the effects of special relativity. And question C is an extremely difficult calculation to calculate the speed of these muons and what speed they're actually moving at. And we know that they're moving at nearly the speed of light, so it's probably greater than 0.9 light speed. That should give you an indication of your final answer. So if you fancy solving this problem, pause the video now and go and try it, and then if not, here is the solution. So the first question, we know that the muons are moving at close to the speed of light, which is 3 times 10 to the 8 as per the IB data booklet. And then it's actually a pretty simple calculation. You just need to make sure you pick the right time, because it's talking about the muons reference frame. In this frame, show that they've travelled 3.5 kilometres. So to the muons, this 10 kilometres distance is only seen as 3.5. Okay. So next question, question B, we have to show how the concept of length contraction applies to the muons. Well, we already have a sort of indication of that, okay? So at relativistic speeds, distances become shorter. This is effectively the effect of length contraction. So in a reference frame of the muons, we need to give, for an extra mark, a little bit of context and application here. This means that 10 kilometres, the muons only experience is 3.6 kilometres. So if you were travelling at close to the speeds of light, the distance between Earth and Pluto would be a lot shorter. That is length contraction. Next up, time dilation. So, in the reference frame of the muons, time moves slower according to the reference frame on Earth. So, time seems to flow faster on Earth and slower for the muons because they're moving at relativistic speeds. So, time periods are slower as measured on Earth, and less time has elapsed in the reference frame of the muons. Okay, so it's important to get the distinction between the reference frames, and for these 2 marks, just make sure that we give a little bit of context, a little bit of detail there, and show that we can apply the concept of time dilation. Now the last question is last problem is definitely a bit of a brain teaser. So we have to determine the speed of these subatomic particles. And we already know that we have the distances, the original length, 10 kilometres, and the length in the reference frame of the muons. So we can use the length contraction formula to calculate the gamma factor, okay? and that gives us a gamma factor of 2.77. From there, we can put that back into the original formula for the gamma factor. Okay, and with a little bit of algebra, a little bit of rearranging, remember that square root of 1 is 1, if we insert our known gamma factor, we can work our way through the problem. A little bit of a square root here, that gives us 0.933. We rearrange the v and the c, and that gives us our final answer, 0.93 the speed of light. There we go.